That's also important to know your electromagnetic spectrum anytime you're dealing with spectroscopy. Right? We should be familiar with that already. Okay, let's finish this up with some miscellaneous things. Good applications. I think we're looking at indicators. Okay? Back and forth. We have pH indicators. There's other types of indicators. Basically, it's a change in structure, depending on what pH you're at or some other type of conditions. Make sense, though? That carbon's tetrahedral, there's no p orbital. So 3 isolated benzene rings. Here, you've got conjugation all the way through here. P orbital's lined up all the way through, and it becomes one system. That p orbital there makes all 3 rings conjugated together. It's like the link that's connecting all 3 benzene rings. Lots of conjugation over there, making the HOMO to LUMO transition easier, and thus longer wavelengths like doing that. It turns out that light that does that is invisible, and if you absorb visible, you're going to be colored. Where the light that does anything here is apparently only in the UV. And if you absorb UV, you're not going to create a color. If you absorb only UV. Okay, steric effects. Let's look at this interesting example. This is called a chalcone. The difference is this one's trans-alkene, this one's cis-alkene. That one has a lambda max of 300 nanometers, this one 280 nanometers. Why is this one lower? Can you give an argument for why this would have a lower lambda max? First off, what does it tell you that it's lower? What does that mean to you in terms of?
Higher energy.
That is a higher energy, and just further explain.
It's shorter.
Do I?
The wavelengths are shorter.
Yeah, but I mean, but explain what's going on. What do you mean higher energy? That's just a statement. Higher energy, what? Thus.
Less stable.
Thus what?
Less stable.
No, we're not really looking at
Would you say that there's less
stability.
conjugation?
We're looking at electron excitation.
Less conjugation.
Yeah, that's what it means. But what do you mean by higher energy, though?
When you know it's higher energy, looking at the numbers, so you know that there's going to be less conjugation.
Okay. Why do you know there's less conjugation?
Because conjugation is what leads to a higher lambda max.
Say that again.
Because more conjugation leads to a higher lambda max.
Okay, let's just do that. More conjugation leads to higher lambda max. Now we're saying more than just 2 words. We're explaining, right? Okay. Need to be able to explain. Not only verbally out loud, but in your mind. Everybody's explaining this in your mind right now? This is the process of you understanding. You've got to talk to yourself. Okay? Yes, it means to me that this has lower conjugation. But why? It's the same. It's the same, except for just one's position like this, the other's like that. I mean, they all have the same number of p orbitals. I got a benzene ring conjugated with a double bond. That's conjugated with a ketone. I mean, why does one? So what's going on here? Why? Do it.
When the bottom one flips up to be cis, it doesn't interact with the orbital ring. Like opposite direction.
But what's going on here is there's an H here. Yeah? And these two are clashing. And what's that going to cause? Instead of these sitting like this, by the way, for them to be fully conjugated, the p orbitals have to be, this is cross-conjugated. If you just want to consider the conjugation here, p, 6, 7, 8, 10 p orbitals, all lined up like this, okay? Consider 10. There's 2, 3, 4, 5, 6, 7, 8, 9, 10. And they're all interacting here, side by side. But let's just consider, there's 2. And then what happens, these two nuclei are repelling each other, and it's going to cause this to go in real life. And what have we just done? Are these all still interacting? No. Now there is some gray area. I mean, we say this is interacting side to side, right? And this is not. Well, what if they're like that a little bit? Are they interacting?
Well, yeah, just not as much.
Right, yeah, but not as much. And so there is some gray area in conjugation. Fully nicely conjugated, not quite as much. Because the electrons are not completely overlapping and interacting. Okay? And this is why the number is lower, because on the surface it looks like the conjugation is the same. What this tells us is something's going on to make the conjugation less down there, and what it usually you would want to, the reason it's usually discussed is probably some steric interaction causing these molecules to not be planar and all the p orbitals interacting, but they're like, they're avoiding each other. So UV vis information can tell you something about structure, true structure. Not just structure on the board, which is not always correct, or which is not always fully informative. UV vis allows you to study the conjugation, something that we can't just easily see. But you can see the absorbance from the instrument. Make sense? What color are these compounds most likely? I gave you lambda maxes. That is the point of highest absorption. The maximum of absorption, what type of light? UV or visible? Yeah, because it could tail off. Here's the max, but as it tails off, you could go into the, But the maximum absorbance is in the UV. Based on that, what do you think the color is? Colorless. And usually colorless could also be white, depending on how the crystal reflects. Yeah. Actually, one of these is sort of almost pure white. The other one's got a tinge of, it's like dirty white, off-white, just a touch off-white. Even in the purest form, it's not snow white. Which one do you think has a tinge of color?
The top one.
Yes, the top one, because it's 300. If we go back and look at something like maybe here, the maximum may be way over here at 200, but that doesn't mean it can't, maybe you get a little bit of absorbance into the visible. And that little bit of absorbance is going to give you a little bit of color. And instead of snow white, it's kind of an off-white. It's like a little bit of, like if you take white paint and put a drop of yellow in it, is it going to make it yellow? No. It'll just start making it sort of not pure white anymore. All right? Make sense? Yes, I know these compounds. This one is not pure white. Where this one tends to be more, certainly in terms of your theory, you'd expect this one to be more pure white, if there was a difference. Okay. Ultraviolet can be damaging to the eyes. Okay. Remember when we had the eclipse last fall? I'll put this slide in there. Don't look at these. Don't look at the sun. A lot of UV coming from the sun can damage your eyes. All right. You can look at this if you're interested. These molecules are in your eyes. Aldehyde. Such molecules come from vitamin A derivatives. Okay. Which, by the way, beta carotene can be converted to vitamin A derivatives. Eat your carrots, right? All right. These compounds, yeah. Such compound, you can look at this. It's basically, ultimately, when a compound absorbs UV, it absorbs the energy. What can happen? When now the compound sits at a higher energy level, and lots of things can happen. That molecule at that high energy level could undergo some type of chemistry. Maybe it's chemistry we don't want to happen. And that's what happens in the eyes. When intense sunlight, you get some chemistry taking place. You can look at this. And then oxygen comes in. You've got oxygen around your eyes, right? Oxygen's actually bad for you. It leads to aging. It leads to lots of problems. But you can't live without it. Okay? It's good and bad. You can take a look at that. It's just some of the biochemistry behind eyes and how UV can damage the eyes. Okay? Now, is this going to be on the final exam? I think you know, right? Showing the applications. Here's another application. You guys ever see bioluminescence in biology?
Mm-hmm.
Like this is a jellyfish. Okay? How does it produce the light? It's fluorescing. What is fluorescence? This is where if something, again, what happens after the compound absorbs UV? Here we go. You excited up here? Does it stay up there forever?
No.
Or does the energy come back out? Yes, it can relax and the energy then comes back out. But how does the energy come back out? It can come back out as heat. It can come back out as light. But what happens though is you absorb UV, but while it's up here, it can fall down to some level by some other mechanism. Okay? Then when it drops back down, it's not dropping as far, and so it's less energy coming out at this point, because some other energy came out some other way. Absorbs UV, but then it re-emits visible, which is lowered energy. And that's what's going on with fluorescence. Absorbs UV, but then re-emits visible. And then we can see it because visible light's coming out. How does the jellyfish get UV?
The sun.
From the sun. Now the UV of the sun can go through the water a good bit. I don't think you're going to find any bioluminescence on the ocean floor. There's not enough UV down there. Closer to the surface. Okay. Anybody know tonic water? What does it contain? Quinine? Compounded mechanism, like the advanced mechanisms. If you shine a UV light on quinine, it'll be blue. Go buy some at Walmart and then shine a UV light on it. Why? Because quinine it absorbs UV. And it fluoresces. Not all compounds will do this magical fluorescence. Some do. You'd have to figure out why do some, why not. But quinine is known to. It's actually one of the first compounds to be shown to fluoresce. People back in the early 1800s were like amazed that this light was coming off. Put in the sun and you get this light like it's glowing. You can do this today. You go to Walmart and buy you some. Shine a light on it. absorbing the UV, but then it's giving back off some visible light. Yeah? This shows two different type of spectra of quinine. The first is the ultraviolet absorbance. This is what it absorbs, with the lambda max being what, right here? About what? Almost 350, right? Lambda max. But this graph is showing what it emits. Okay? An emission spectrum. You can graph that as well. It absorbs this, but emits this. And what range is it emitting in?
Visible.
Yeah, it re-emits visible. This is a wonderful phenomenon, absorbing UV and then re-emitting visible, called fluorescence. Okay, that was it. Any questions about UV vis? Everybody get a handout, bromination handout? You can turn in your last lab, double E2. By the way, somebody tried a new solvent for this reaction. Actually, 2 people did. You tried, okay, everybody used 2-methoxyethanol. Okay, it's a little toxic, boiling point's about 125. Because it's a little toxic, I'd like to maybe try to find another solvent. All right, somebody tried methanol, boiling point about 65, and the reaction didn't work. Actually isolated starting material, got back starting material, some, small amount. Wasn't fully analyzed, but didn't see much evidence of product. Although there could be some other things. Certainly didn't work as written. You can't just replace it with methanol. All right. But then yesterday, or the day before yesterday, somebody else tried what solvent? 1-propanol, boiling point of 98, almost 100. Boiling point of 65 didn't work. Boiling point of about 98 to 100 did work. Nice. Actually, the product was more white. Right? Most of your products from here had a tint of like orange. You know, the pure compound is pretty much white. The tint of orange is some impurity. It did not come out even with recrystallizing. Maybe if you recrystallize again a couple of times, okay. But you got a near pure white compound, first recrystallization, and the melting point was good, decent yield. Looks like 1-propanol does work. 1-propanol is less toxic, has an NFPA rating of 1, where methoxyethanol has a rating of 3. Most any organic is going to be at least 1. 2 is a little bit, 3, but too toxic for me. Something with 4 you would never be using in lab here, not in a teaching lab. Okay, I'm going to turn those in, pass them to the center. So in the future, I've already changed the lab. In the future, students will be using 1-propanol. Boiling point of just under 100. Yeah, everybody got double E2? Everybody?
I know. I'm super good.
Again, group lab will be returned this afternoon. Let's take a 2-minute break and then we'll look at bromination. Radical bromination.
Is it the heavy light for fluorescence, and how does that work?
How do what?
Egg. like
That was
no.
a mistake, my test back.
They control when what is it? What releases that energy.
Steven, I have a question. So
Uh-huh.
you said that like jellyfish, they light up because of like UV rays that like, you said that jellyfish light up because that they're like high enough in the ocean to get the UV rays from the sun. So what about that like fish that was in Finding Nemo that has a
Anglerfish.
Yeah, the anglerfish.
They don't know. We learned about it in micro. They literally have not figured it out because they can't, what is it? They can't breed it in captivity or something. They literally can't keep the thing alive to.
But Dr. Bates said it was some type of bacteria or something.
Yeah.
What is the question?
Yeah, but see, they're not getting light either.
Like, so the anglerfish, like, it has like a little, like little thing on its head.
You know, the thing that flashes.
It's got a
and
light
then-
bulb?
Yeah, and then fish are like, ooh, pretty light.
It can't go near the surface? Now, okay.
No, they're like 1,000 miles deep.
I assume that, okay, sometimes I make these statements, they're not like handed down from, it just seems reasonable, you gotta be near the surface to get the sun, the UV. You don't see as much bioluminescence near the bottom, but you're given an example. So what's that thing goes nowhere near the surface?
No,
No.
it's only like in the deep ocean.
Yeah, they can't go any higher up. It'll kill them.
So what is some of the explanation, potential?
Are we talking about bacteria?
Yeah, Dr. Bates taught us in micro last semester that it's actually the bacteria living in the little lamp thing. But then how do the bacteria fluoresce?
Well, there's other mechanisms for fluorescence, I think, and bacteria can produce, well, I don't know the exact answer, all I can do is give you some possible reckoning. Bacteria can produce compounds that, when they're produced, they're at the excited state. I mean, you can move an electron to a higher state by ways other than UV. And maybe the bacteria are producing excited state compounds by some other way. And then they fall down by giving off light.
Yeah, because they don't know the exact mechanism. Just because they can't keep the fish alive too, and the bacteria to be able to do it. But
Jellyfish control what it fluoresces.
Can they control it? Actually, well, again, I know very little, but I've seen like responses,
Yeah.
like you flight or fight or whatever, adrenaline, whatever the molecule is, that can lead to more of this.
but you can't really control that.
So why is it that like neon colors reflect more than?
Well, hold on, before you get there, you can control, because what in the jellyfish is absorbing the UV? It's not just the jellyfish. There's molecules in the jellyfish or whatever they're doing this. Everything molecular based, okay?
I mean, you can't.
Even in your
like,
body,
control
cancer,
that.
it's all molecular based. The molecules, that's why molecules are so important.
Yeah,
Why it's so
they're gonna
important to
go-
understand what molecules do. That's why organic is a prereq to medicine. Okay, the molecules though, what happens if you are in a dangerous situation, your body produces more adrenaline? Okay, well what if adrenaline is the thing that fluoresces? You produce more adrenaline, you're going to start fluorescing more. Okay, there's some molecule, or maybe it's a collection of molecules that are absorbing and fluorescing in the jellyfish.
It's like a pre-programmed function. Do that.
You're getting above me. I don't think that's an organic chemistry term. A pre-programmed function,
For biology.
that sounds like biology. Sounds like genetics or something. I don't know. Just like adrenaline, you got adrenaline pumping through your veins because your biology, biochemistry can produce compounds at certain times, and maybe these compounds fluoresce. So yes, it can be controllable, I think. I've seen a little bit of that. What was the other question?
Like why does like a neon yellow shirt fluoresce more than like a regular yellow shirt? Like if you're under a black light.
Yeah.
Well, again, it boils down to certain molecules in there. You know, you can take certain paint and put in certain molecules and then it's going to fluoresce because of those molecules.
Oh, it's apparently the proteins that fluoresce.
Not all molecules fluoresce. Most, I think, many or almost all, I possibly could say, do absorb UV, but not all then re-emit into visible. You know, only some do. Some may just re-emit UV, I reckon, or some may re-emit just heat. I don't know, there's other mechanisms. And then you say, well, why the difference? Well, that's organic chemistry. That's, some of that is known and some of it is not quite known yet.
Right.
Yeah.
What are the structural features of compounds? What are the structural features of compounds that make them fluoresce? The more that's known, the more you can design compounds. Have designer molecules. A lot of that's being done.
They do that with some of the fish that they sell at like pet stores. They somehow do the genetic modification to where the just regular fish that don't usually fluoresce, they can make them fluoresce. They're called,
Yeah,
like,
I mean, that's
navigator
genetics.
fish.
I've had some of that.
In that scenario, you really don't have to know anything about molecules. You really just modify genetics. That's nothing wrong with that. On the other hand, if you knew what molecule it was, I don't know, maybe you could then start putting it in the feed. Well, then you got to know metabolism. Is it going to be metabolized? Well, then you have to know biochemistry and what type of metabolism is possible. What I'm trying to get at is, this is the stuff you're studying, because then you can go on and design designer molecules to make your fish fluoresce, if that's what you want to do. Or you can go cure cancer if that's what you want to do.
Yeah, that sounds more applicable.
That sounds more important than making fish glow?
Well, I mean, I don't know. It depends on where your priorities are, but
Well, it all
cancer is
depends.
probably better.
You never know what opportunities or interests are going to come up. I guarantee you, not everybody's going to cure cancer. We need glowing fish. It makes life better to have such good interest in stuff,
Maybe they
right?
could save the ecosystem of the oceans.
Is it happiness?
Okay, guys, let's look at this here so we can move on. Document camera. Okay, what have we done here in this course? What have we learned? Now, hopefully we learned a couple of things. Hopefully learn what a mechanism arrow shows. What does a mechanism arrow show?
Movement of electrons.
Uh-huh. Was there an extra handout? Thank you. Yes, that came today. Hopefully we'll learn what bases do. What does a base do?
Takes an H. Steals an H.
It takes, yeah, it doesn't donate. It doesn't accept an H, right? It takes H's, right? All right. What else have we learned? We learned that carbocations are pretty common, and the best type is what?
Tertiary.
Tertiary. What if it was tertiary and resonance stabilized?
Even better.
Even better. Okay. Hopefully, we learned a few core things of basic introductory organic chemistry. All right. What type of functional groups have we been doing chemistry with? We started with alkenes, other than acid base. Alkene reactions, very important. Alkenes, we did alkynes, they're twice the fun. Then we did, in general, substitution elimination reactions, very versatile. In general, that can be called leaving group chemistry. Both of those have neat leaving groups, substitution elimination. Okay? So, alkenes and things with leaving groups. What about an alkane? What type of chemistry can you do with an alkane? Can you do alkene chemistry? No. Can you do substitution elimination? No. When we did alkane handout way back, I told you there's only two things you can do. You can burn them in your grill, combustion reaction. It's a radical oxygenation. But I also told you that you can do radical halogenation. And radical halogenation can be more controlled. You can just do one halogenation. And that's really all you can do with alkanes. It's useful. But we need to look at this radical halogenation. And the most common is to use bromination. Because the thermodynamics turns out is just right, just good for bromination. Mother Nature gave us bromination. Radical bromination is a good reaction. Radical chlorination, not as good. Because it's not as selective. You try to do chlorination, you're going to get mixtures of products. Sometimes it can be done and purified. But in general, radical bromination is the best. Why? Because chlorination is so exothermic. You can do calculations. So exothermic, so it's like a bull running through a china shop, just reacting everywhere. Bromination is a little bit less exothermic, so it's more moderate rate, more selective. Okay, boom, I'll react here instead of everywhere. Iodine, on the other hand, is too lazy. Why? Because the CI bond is weaker. And it's hard to do iodination. Actually, iodination tends to go reversible. Iodine typically comes out. Go back to alkanes. What about fluorine? Well, chlorine is bull in a china shop. What is fluorine?
Gonna blow
You
up.
better stand back, okay? Working with fluorine, dangerous. Super exothermic. Why? Because the CF bond is so dang strong. It all comes from calculations. Again, the calculations turn out that your bromination just is the best. Good rate. So that's why it's the most common, and that's what we're going to be looking at. Okay, here's a type of reaction. You just take an alkane. We can react this with elemental bromine. But it's not an alkene. It's not an addition reaction to an alkene with a bromonium and a backside attack. None of that. It's a different mechanism. And it's not just a simple addition. Yes, we are adding a bromine, but what type of reaction is this overall? It's actually a substitution because we're replacing an H. So you don't call this an addition reaction. It's a substitution reaction. And here, what else would we form here, just to finish up a balanced?
HBr.
Yes, it's also going to create HBr. So that's the fate of the other bromine. This reaction tends to be very selective. What carbon did we brominate here?
Tertiary.
Tertiary carbon. We have terminology we know. Yes. Very selective for the tertiary site. Again, compared to this. This is our good old bromination. If we had stereochemistry here, we know the bromines would have been had an anti. That's an addition reaction. This reaction is very easy. No extra energy is needed. It's exothermic. Transition state is also pretty low. Room temperature, the heat. Some of you guys sometimes think that room temperature means no heat. No, there's plenty of heat present right here. If there was no heat, it would be absolute zero. The heat at room temperature is enough to make that reaction down there go. You can even do this at cold temperature. I don't think it worked at absolute zero. This reaction, on the other hand, requires some more energy. It either requires light energy or heat, delta heat, or peroxides. Okay, so we need a little help up here. Here we're going from pi bond to 2 strong sigmas. Here we're just going from one sigma to another sigma. Right? Mechanism for the top reaction. It's a radical reaction. We don't have a pi bond. We don't have a lone pair. So you don't have a classical nucleophilic site. The first step. The bromine. It's covalent. Heat or peroxide. Let's use light energy. Okay. Light.